All right, I'm going to start up again, even though some of us haven't made it back yet. So today's next section is on how to calculate some more complicated events probability, right? And either of these are too bad. Students can get lost in the weeds on these, but like the intuition for it is simple, right? So what are the things that you should know that you should be able to do? You should be able to calculate the probability of compound events. Has anyone heard a scene, a Venn diagram before? Right? I think most of you have probably seen one. I'd be surprised if somehow you just hadn't seen one, but it's not, right? So we're going to use Venn diagrams that will help us give some intuition about probability rules. We're going to distinguish between independent and dependent events, right? They kind of sound like what they are, but students do get lost with that sometimes. If this one you're like, hey, I'm kind of shaky at it even after doing the homework in this, that's not the end of the world, because we will do a lot of conditional probability, independent, dependent events in the next section. But this is something that overall is very important. And you use the multiplication rule, which requires you to understand the difference between independent and dependent events, because you need to use different rules. So a compound event is the intersection or union of two events. So we're not talking about outcomes, right? So when we're talking about outcomes, since outcomes cannot be broken down any further, outcomes can't be overlapping, right? But events can, right? So for example, the event roll a 6 or a 3, it overlaps with the event roll an even number, right? Because there are some ways you could do both, right? I could roll a 6, right? So the union of two events is all events that are outcomes for either or both of the events. The intersection is all outcomes shared. Two events are considered overlapping if they have one or more outcomes in common. I will come back to union intersection, so don't worry too much about the definition. Just mostly understand it in a little bit. Okay, mutually exclusive events have no outcomes in common. You can also call these disjoint. That's maybe a simpler way to say it, right? Mutually exclusive, the word mutually means it's both ways, right? If you have romantic feelings towards someone and it's mutual, right? That means wedding bells are in your future or whatever, right? So mutually exclusive mean each event occurrence excludes the other event from occurring, right? Disjoint, the events cannot occur at the same time. Anybody can give an example of two events that are mutually exclusive? Events that cannot occur simultaneously. Not too difficult to come up with mutually exclusive events. Two events that cannot occur simultaneously. Very easy. Come up with some example. All right. Well, there's a big event this weekend. It's the Super Bowl. So here are two mutually exclusive events, right? That the Chiefs win and the Niners win, right? Those are mutually exclusive events, right? Or I assume the Super Bowl is going to happen, right? There could be the worst windstorm in the last 1,000 years. So two mutually exclusive events would be the Chiefs win and the Super Bowl is canceled or postponed or something, right? Those would be examples of disjoint events. The occurrence of one precludes the other one, right? Some are much more, they're pretty straightforward, right? Another example of mutually exclusive events would be I flip a coin once, I get a head, flip a coin once, I get a tail, right? Those are mutually exclusive events, right? What is the union of two events? The union, right, which we mean by A or B, are all the outcomes for either of the events, right? So these are some outcomes, right? Right? These are two events, right? Event A seems to have 9 different possible outcomes, right? Event B has 8. There seems to be 4 outcomes that involve A and B occurring, right? Any of these 13 outcomes would be the occurrence of A or B. Right? So if I say, if you were here yesterday or you were here last week or the week before that, stand up, you would stand up if you were here last week, if you were here the week before, or both, right? So notice the word or in mathematics is more like the word and or in everyday language, right? If you're at a restaurant and they say, would you like a soup or a salad, right? That means you have to choose one between, you have to choose exactly one of them, right? In mathematics, you would be able to take both, right? So we really use the word or, right, as it's not really a word, but sometimes we say and or to mean, right? That is the definition of the word or in mathematics. So that's called the inclusive or. So that's union, right? Union means together. And you would say with or. Intersection means both have to occur together, right? So these 4 outcomes would be in the intersection. These would all be in the union. Intersection is easy to me that it's the and because it is where those 2 circles intersect. Now, mutually exclusive events have no outcomes in common, right? So I said the Niners and the Chiefs winning the Super Bowl, right? Those are mutually exclusive events. So the probability of both the Chiefs and the Niners winning the Super Bowl is 0, right? Because they are mutually exclusive events. In terms of a Venn diagram, it would look like this. Here's 2 mutually exclusive events. Drawing an ace, there's 4 ways that could happen. Drawing a king 4-way, none of the ways, there are no cards that are both an ace and a king. So these would be considered mutually exclusive events. If I told you Regina drew a card and it was an ace, you could tell me with certainty that it was not a king, right? And vice versa, because these events could not occur simultaneously. These are not mutually exclusive events. We use the word for this overlapping. These are events that can occur simultaneously, right? So drawing a heart and drawing a king, for example, right? If I told you, right, Emma drew a heart, you would not be able to tell me whether she drew a king or not, right? You can, so just to think about it, right? So the union of these 2 events would be drawing any of these cards. The intersection of these 2 events would be drawing the king of hearts. Questions between intersection and union, right? Intersection is both occurring. Union is either occurring. All right, now let's see how we find the probability, right? So if I want to find the probability, right, I'm going to give you a formula, guys, that there's an intuition. You need to understand the intuition, but you should have this formula memorized within an hour of this class because it is that important. Probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. What's this tuition here, right? Think about a Venn diagram. This might be event A, this might be event B. I want to find the probability of A or B. So that's anything. This is A or B, right? Well, straightforward approach would be, all right, what's the probability of drawing a heart? Well, or a king. Well, I'm going to add the probability of drawing a heart to the probability of drawing a king. Well, the problem with that is if the two events are overlapping, you are double counting some outcomes, right? So to adjust for that, you have to subtract the overlap, which is the intersection, right? Let's just look at that, all right? Anyone know how many cards are in a deck? 52, right? So let's say we want to find the probability of drawing a heart or a king. Well, we could calculate it, but here are all such cards, right? Let's see here. How many cards are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So there are 16 favorable outcomes out of 52. I could reduce that, but I'm not going to for the sake of this demonstration because it is not helpful. Sometimes that happens and I don't know why. We'll do a couple more of these, right? Well, we know we should get 16, right? Now, how many hearts are there, everybody? 13, right? So, right, including the king. So they're 13 out of 52. This is the probability of drawing a heart. I could add the probability of drawing a king, and that seems that it would give us the probability of drawing a heart or a king. But this is going to add up to 17 out of 52 because notice it is double counting this outcome because it belongs to both events. So to adjust, you have to subtract what you counted twice, right? Everyone's saying that that's the correction. So notice this is P of H plus P of K minus P of H and K. So the OR is the sum, the two parts, minus the overlap. So the union, right, is the sum of the two parts minus the intersection. That's all this formula on the previous slide showed you. That's what this rule says. You can reason through this rule. Don't need to memorize it, but it'll be much easier if you do. I've done both myself but I can recall this rule by the intuition from it, right? And understanding the notation. At your point, you should just memorize this, and you need to memorize this quickly because it becomes important, right? There's only a couple things you have to memorize in this class, just like straight up memorize formulas, right? I don't ask you to do a lot, so please memorize the ones that I do ask you. Now, if A and B are disjoint means that the rings don't look like the Olympics. They're like this. If you have disjoint events, there are no outcomes in common. So in that case, you can just add them together. Now, this isn't really two formulas. Because in this case, if you have disjoint events, what's the probability of the two events occurring at the same time? 0. So notice I could still subtract this because that just happens to be equal to 0 when you have two disjoint events, right? So this event is always true. This rule is only true for disjoint events, right? So if you memorize, you never need this second rule. You can always use the first one, right? Because it is more generally applicable, right? Questions? Seems straightforward to me, right? I mean, it might take some chance getting, I feel like you all, some of this probability stuff, I don't know what it is to say. Like it's straightforward. You all have this intuition. You've been using rules like this your whole life. You just haven't formalized it, right? So that's harder. When I say it's straightforward, I don't mean that it's easy. I mean, somewhere in your mind, you know this. You just have to pull it out and formalize it, express it in statistical and mathematical language, and then you can rock hard in this class, right? That's what I'm just, there's something in there, you just need to pull it out. Now, most of you probably already know this. This is just the organization of what's in a deck because we use these for probability problems. You do not need to know, I will never refer to any rules of any specific card games, right? All you have to know is what is in a deck, right? So there are 4 suits, right? 2 black suits, right? Clubs and spades, 2 red suits, hearts and diamonds, right? There are 13 cards in each suit, right? Instead of a 1, it's an ace, and then it counts up to 10. And then there are 3 face cards in each suit, right? Which are considered the jack, the queen, and the king. These cards are considered face cards. So these 12 are considered what we call face cards. So, right, you can think about it as using, I'm going to show you what I mean, right? You can use either, you can think about the second formula as being its own thing, or you can think of it as not really a formula, right? It's just part of the first one. So here's a probability. You got a standard deck. What's the probability that a card is a 10 or a face card? So are these considered overlapping events, ladies and gentlemen? This is an easy one. Drawing a 10 and drawing a face card, are these events that overlap? Here are the 10s. Is that overlapping with the face cards? No, definitely not. If you're thinking that they can, you're thinking of drawing 2 cards. I'm talking about drawing 1 card, not drawing 2 cards one after another, okay? Notice that it says a card is drawn. Read carefully, right? So the answer here, guys, are these overlapping events? The answer is no. Since they're not overlapping, they're mutually exclusive events, you can just straight up add these probabilities. How many outcomes are there for 10? You guys know this. How many different outcomes? 4, right? Very good. And for face card, there are 12. There are 3 faces, the king, queen, and jack, and there are 4 of each, right? So there are 12. So probability of A, drawing a 10, is 4 out of 52. Probability of B is 12 out of 52. The probability of the or, sorry, I have a symbol here that this symbol right here means or. I will not use it. The textbook doesn't. I tried to get rid of it in all my old slides, but sometimes I forgot. So just change that to or. You just add these probabilities together and you can reduce and rewrite as a percentage, right? Notice this is only possible because these events are disjoint. But if you don't want to think about, right, are the events disjoint or not, I just want to use the formula, we can adjust this formula. To include the intersection. But it doesn't really matter here because what is the probability, guys? Again, remember, It's one card, right? What's the probability of drawing a card and it both being a 10 and a face card, everybody? This is the easiest question you're going to get. What's the probability of drawing a card that is both a face card and a 10? Everybody? 0, right? Aren't there, it's a face card and a 10, right? So that's a 0. So you can include the 0 in the formula, right? If you subtract P, the overlap, right, you will not be in trouble if there is no overlap, right? So I suggest you memorize the formula that involves the overlap, right? Because that's the only formula then you need to memorize, right? Okay. These, I'm drawing one card, right? That's the thing you got to remember. I want to find the probability that is a face card or a spade, right? The word or, does that talk about the union or the intersection, everybody? Or is the... So here's the union of two circles. Am I in A and B or A or B? Or, so this is the union, right? So or always means union, guys. This is something I just showed you. Okay, but are these considered overlapping events? Drawing a face card and drawing a spade are overlapping or not, class? Overlapping. So we have to use the fact that they are overlapping. So there are 12 face cards. How many of those are also spades? 3. And there are how many spades? 13. So here they are. Probability of A drawing a face card is how many face cards out of how many? Face cards, there are 12 out of how many total? Probability of drawing, do we get, I'm not getting a lot of, do we get the prop 12 out of 52? Right? I'll skip that one for it. There are 3 that are both, so this is the and. The probability of A and B, the intersection, is 3 out of 52, correct? The probability that it's just a spade is 13 out of 52. So if I want to find, and again, I keep forgetting, I need to change these. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of both happening simultaneously. Why do we subtract? Because those are double counted. And you can reduce this and make it a percentage. All right, class. Let's come together. Is there anything about this rule that you need to ask about now that you tried to describe it? Anything that's not clear? Now, this rule down here, is this rule true for every scenario? No, because this requires them to be disjoint. What about this rule up here? Is that one always true? Always. That top rule is always true, right? A or B is always A plus B minus the overlap. Sometimes that overlap just might be 0, right? So you can get away with only using the first rule, right? That's the only formula I've taught you pretty much all day, right? So please memorize this, right? It will make your life much easier if you memorize this right now. Okay, so I just want to give you some things that you can think about, right? And that you can talk about. So conditional probabilities, right? It is well known that certain events affect the probability of other events, right? So if you're right, so certain things, being unvaccinated affects the probability that if you catch COVID, you will die from it, right? If it is cloudy outside, that affects, right? If you look outside and it's cloudy, that affects the probability that it's going to rain, right? When I look outside and you say, I would say, I'm like 95% sure it will not be raining in 20 minutes, even if I didn't look at the weather report, because I don't really see many clouds, right? The clouds I do see are cirrus clouds very high in the sky, right? So if I know that the probability it's raining at any given day or any given moment is 10%, that's not particularly useful to me right outside, right? Because I would say, then I shouldn't operate, right, that the probability that it's going to rain 10 minutes from now is 10%, right? Because it's not cloudy. There's not a cloud in the sky. I'd be way overestimating the probability of rain. You guys feel me on this, right? So these are what we call conditional probabilities, right? If I look outside right now, right, it's not cloudy right now, but let's just suppose it was, because that's the example I have up there. If it was cloudy outside and I wanted to know whether to expect rain, I would need to know, what's the probability it's going to rain if there already are clouds outside, right? So what I want to know is the conditional probability. What's the probability that it will rain if it is cloudy? And the way that I write that mathematically is with this vertical line between the two things, right? Which you can read as if when you read it out loud, or you can read it as given. I would typically say given. So read this as probability of A given B, or probability of A if B is pretty close. Do we get the idea that probabilities are conditional, right? There are so many events out there that we know, right? Things are likely, right? I mean, it's not noticed you if you watch any basketball game of people that are at any level that is competitive, whether it's college, NBA, WNBA, there are a lot of tall people there, right? So the probability of somebody being a professional athlete, professional basketball player, is very low across the board, right? But it's probably much higher if they're over 6'5", right? So conditional probabilities are important. Now, certain events are independent and dependent, right? So for example, I would say being a great basketball player is definitely dependent on your height. It's not a one-to-one thing, but being, right, one event occurring affects the likelihood of the other one. Now, being tall is not likely to, it is independent of being a good chess player. Being tall does not hurt your ability to play chess or help it, right? So that's an idea of independent events. So two events are independent if the occurrence or non-occurrence of one effect does not affect the occurrence or the non-occurrence of the other one. Two events are dependent if they do affect each other, right? All right. I need to change this at some point. Okay. Anybody want to give me an example of two events that are independent? Just two events where the probability of one event does not affect the other one. So just think about, yeah, go ahead. Yeah, right. So you might want to, you mean the outcome, like a particular, like the Bulls winning, right, on their next game does not affect the Bears winning their next game, right? In any, right? So those are two events that are independent, right? The knowing how the Bears, if the Bulls game happens first, right, which it would, the Bears aren't playing for quite a while, right? That's not going to help you make a prediction on the other one. So that's independent events. Anybody else, right? Bobby participates a lot. Want to give me an example of two events that are dependent? So one event, knowing that one event occurs or it doesn't occur, affects the probability of the other event occurring. Yeah. So I would say there could be some reasons you might, right? So I would say the probability that the event Regina takes aspirin is dependent on the event Regina has a headache, right? And it's right. There's obviously one way of causality, but mathematically we can't really look at that causality, so we don't really need to worry about that, right? We just know that when one event occurs, the other one typically occurs with it, but not all the time, right? So those are two events that are independent, right? We will just, let's see, I won't really talk about this first one because it's too much, but I will stop after this one. So I want you to focus on this first rule right now. You can write down the second one. The first rule has some intuition, right? Notice here it's E, F, and E. It's not any different if it was A and B, right? Or whatever events you want to choose, right? So let's use these. I do not follow basketball. So let's do Bobby's things, right? So F can be the probability that the Bulls win their next game. I'm going to abbreviate that to Bulls win, right? And E will be the event that the Bears win their next game, right? Let's look at this, right? So this test, students have issues with, right? For some reason, seeing it written mathematically, this test, I don't need to, it comes directly from the definition, and you're going to see it once you have the example. So since Bob, you came up with this, you're just gonna make up some probabilities for me, right? But you're gonna guess based on. So I will admit I don't follow any basketball at all. I'm a bit of an obsessive person, so when I follow a team, I feel I have to watch all of their games. So basketball would just be too much for me, right? Because I have to watch all of them. What do you think the probability that the Bulls will win their next basketball game is? I don't even know if they're good now or anything. 40%. All right. I don't know if that's right. Let's just go with that, right? Okay. Now let's read this, right? Now, this is not the order, but it's still, you can, backward, you can reason backwards. Like if you know something that occurs, on Friday, right? You could kind of backwards estimate a probability for it occurring, whatever would happen on Wednesday based on that, right? So let's say this, Bobby. Let's say I've got a crystal ball and I tell you that event E. So let's read this. This is F given E. This means probabilities Bulls win their next game given the Bears win the next game, right? So this is saying I have a crystal ball, but for some reason this crystal ball is defective. It can only tell you whether the Bears are going to win their next game. So you have that crystal ball. It says yes. What do you now estimate the probability that the Bills will win their next game? Is it still 40%? Yeah, they're independent events, right? So notice this is true because these two events aren't related, right? If these numbers were different, right? If this number was 70%, right, then somehow the fact that E occurred affects it F. So this is the test of independence, right? Now, you do not know how to calculate this yet. That's the next section of this book, right? But this should be intuitive. If two events are independent, right, like if I wanted to know that, the probability that one event occurs should be the same that event occurs given the other event occurs, because the two events have nothing to do with each other. So if you can calculate both of these separately and compare them, right, equality means that the events are independent, which means if these two things were not equal, they would have to be dependent, right? We all following, right? We all get intuitively that if I give you this, this has to be 40%, right? So if I have both, I can compare them. Yes. Correct. And not correlate, I said that because I want to give you some intuition. We call that independent. Now, guys, just let me remind you some things. So your celebration, right? Wednesday, bring your graphing calculator. Bring your note sheet, right? Also, bring your whatever notebook, old-timey papyrus scroll, whatever you've been using to assist you doing the homework on MyLab, right? Bring that. I will check just to see that you've been writing down. No, I'm looking at your notes to see if you've been doing your homework on paper in addition to doing it online, which was on the syllabus. Yes, yes, please take that. Yes, guys, and if you want to stay and ask me questions about the practice celebration, the answer key's online. I will put it here. You can stick around. I will be willing to stay here up to another hour, but I've been teaching since 8, so past that, no, right? So I will stick an hour. I also have office hours tomorrow from, please don't talk while I'm talking, from noon to 1 and from 2 to, well, no, wait, so sorry, from 1, let me start over, 1 to 2, and then from 3 to 5. Yes, question. Correct. Yeah, I mean, yeah, that's because that's all that's due. I highly suggest that you have homework 3 done by then, right? Because why would you practice stuff after it's assessed, right? But I did not think about that when I set the deadline, and I'm not going to be a dick and pull it back, but you guys know what's the right, the smart decision, right? So let's make good decisions. All right.